best advisors in the world, Baptiste and Willy. We are affiliated with the Université de Neuchâtel, Inria, and the University of Sydney. So let's begin with something that we're all familiar with, prefetch. With prefetch, we move the data up the memory hierarchy in advance before it is needed, so as to reduce the cache miss rate and to improve the overall performance of the application. And pre-store as the new idea we present in our paper, we define it as the converse or the counterpart of prefetch. With pre-store, we proactively move the data down the memory hierarchy before the CPU is forced to do so. And it's very easy to implement pre-store. Pre-store is essentially a function call with a few parameters. For example, the address and the length. And the lines of code of this function, they translate efficiently to existing asynchronous assembly instructions. We do not rely on any new CPU instructions. So now the obvious question is, why do we need pre-store? Conventionally, CPUs were designed to utilize only one type of memory, which is DRAM. DRAM has very low latency and high bandwidth. Nowadays, due to the growing demand of applications, programmers and researchers, we are beginning to seek alternative types of memory. For example, memories that's connected to FPGA, different types of RAM, or even CXL SSDs. These memories, they are very different in terms of characteristics comparing to the traditional DRAM. And in this talk, we are going to look at two types of these memories. Let's start with the memories with high latency. And to make sure that we are all on the same page, I will provide some contexts for everyone. First, processors, they can delay writes. What does this mean? It means that when a processor executes a write, it is usually not immediately written down the memory hierarchy, for example, to the cache, but instead is rather kept inside the CPU registers. Processors can utilize this delay to avoid repeatedly writing to the same location or the memory coherence cost. Another context is that despite CPU likes delaying writes, instructions with fan semantics may force CPU to write earlier than it wants. For example, an actual memory fence or an atomic operation. When this happens, the CPU will spend some time writing down from registers to the cache. And it's important to note that for simplicity in this talk, I will assume that the write is happening exactly at the fence, and we use the time CPU waiting at the fence to demonstrate how long the writing is going to take. And following the previous context, when the CPU is performing the write, it involves accessing the directory of the memory to make sure that the data it's writing to is in the correct state. And the speed the CPU can accomplish this is largely dependent on the memory latency. So this is typically okay for conventional DRAM because the latency is low and the CPU can do it in no time. And therefore, the CPU will not store due to the writing. However, let's think about what will happen if you have a high latency device. The CPU still delay the write for as long as it wants until the fence, and then the last minute write occurs. This will degrade the performance because accessing a high latency device to complete the write will take much longer. And what does pre-store has to do with this? We are going to follow the write with an immediate pre-store. In this case, pre-store will ask the CPU to initiate the writing in the background, parallel to the other things that's running on the core, hoping that the write will be partially or completely finished before the time it reaches the fence. And as you can imagine, comparing to the traditional design, pre-store will significantly reduce the CPU time stalling by finishing the writing in the background in advance at almost no cost, reducing the running time of the application. And now, back to the two types of memory, let's take a look at the second one, which is the memories with different granularity. And even though I think most of us know by now, and again, some context for everyone. Nowadays, different devices, they use different write granularities to achieve the maximum bandwidth and to reduce the cost. Granularity here means the minimum unit for writing. For example, if someone writes 1, 4, or 8 bytes on an Intel CPU, regardless, it's going to send 64 bytes to the device. And now let's assume that the 64-byte cache line was evicted from the CPU. For conventional DRAM, it's going to symmetrically cause a 64-byte immediate write. However, for an obtained persistent memory module, it's going to write 256 bytes instead. And even worse, for a CXL SSD, it's going to write 512 bytes. And this is going to cause the repeatedly mentioned write amplification, wasting a significant amount of resources that's already limited. And to get some deeper understanding of the situation, let's take a look at this simple code example. A memory copy of 256 bytes to a random location of the array is surrounded by a loop. And as a reminder, Intel CPU has a granularity of 64 bytes, and the CPU will break the write into multiple 64-byte cache lines. And as time goes by and as you proceed in the code, the CPU cache will be eventually full of the dirty cache lines, and it will have to start evicting cache lines. However, because CPU caches, they were designed with the conventional DRAM in mind, CPU cache evict data using a pseudo least recently used policy or even a random policy. And therefore, cache lines will not be evicted strictly according to the time they arrive in the CPU cache, but instead they will be scattered everywhere in the timeline. And consequently, this will cause write amplification. And again, let's assume that the underlying media is persistent memory module. Then every distant 64-byte evicted cache lines will cause a 256-byte media write, wasting a dramatic amount of the already insufficient bandwidth. And now let's tackle this problem with pre-store. Similarly, we are going to follow the write with an immediate pre-store. In this case, instead of a random policy, we ask the CPU to write back the cache lines in the quick succeeding order we want. Therefore, by the time they arrive at the underlying media, the media itself typically has the ability to collapse the adjacent 64-byte cache line writes into a single media write, eliminating the write amplification. And now we have finished introducing case 1 and case 2. Let's do a quick recap by looking at the interface of pre-store. For case 1, we follow the write with the pre-store in the background, hoping that the write will finish before it sources the CPU. And for case 2, we follow the heavy write with the pre-store to eliminate the write amplification. It seems like a relatively easy task, but however, it's more difficult than it looks. Imagine that you have thousands of fences in your code, or maybe the writes are not accomplished by a simple interface such as memcopy. It can be a loop, for example. Then the non-trivial problem here is how can we match the previously mentioned two cases correctly against your own application. And this is why we designed Dirtbuster, a tool to assist the use of pre-store. The goal of Dirtbuster is that given application as an input, it should output where and how to pre-store to guide the programmers. The first step of Dirtbuster is a lightweight memory access profiling that can be run online. If the application is write intensive, then it's going to output the corresponding code sections. And at the meantime, we also filter out most of the unsuitable applications, for example, the applications that's non-memory intensive or dominated by read. In those cases, there's nothing pre-store can do. And after that, the write-intensive code sections is going to be passed on to the second step of Dirtbuster, where we use Intel pin to instrument the binary of the application. We're going to precisely analyze the memory access pattern of the application and look for the matching ones. For example, fence after write or potential write amplification. And we also filter out the remaining unsuitable applications, for example, the ones with no matching patterns. And finally, according to the Dirtbuster output, we implement pre-store. Now we have pre-store. we have Dirtbuster, we can start evaluate how well they collaborate. First, we are going to evaluate case 1. We feed Dirtbuster with some key value stores that's running YCSB workload A. The first step of Dirtbuster test is write intensive, and yes, because half of YCSB workload A is writing. And then in the second step, we found that there are fences falling right. It's a common case because fences or atomic operations are commonly found in key value stores to synchronize between threads. And finally, we apply the appropriate pre-store. And just in case everyone forgets, for case 1, we need high latency memory. And thanks to ETH, they built a very powerful machine, Inria. Inria has an ARM CPU that's cache coherently connected to an FPGA. They all have their respective DRAM. And we configure the FPGA to be running in high latency mode. During our benchmark, we access the FPGA's DRAM from ARM CPU to simulate high latency. And with the benchmarks of key value store that's patched with pre-store, we achieved up to 52% faster for a hash table and up to 25% faster for an ordered index, such as trees. And then we evaluate case 2 with a pretty well-known benchmark, which is TensorFlow training. Memory access sampling in step 1 says it's write intensive because during training, it requires to write large tensors. And after the binary instrumentation, we found potential write amplification because it writes large chunks of the memory. And then again, we applied the appropriate pre-store according to the Dirtbuster suggestion. To replicate the scenario that causes write amplification, we are going to use an asymmetric platform that has an Intel CPU of granularity 64 bytes and a persistent memory module having a granularity of 256 bytes. In TensorFlow, we achieved up to 47% faster with small batch sizes, but still we achieved an OK score with large batch sizes, which is around 20% faster. And furthermore, we discussed some more attractive details in the paper. For example, high-performance computing applications, message passing interface, and the other details of Dirtbuster, as well as different flavors of pre-store. And we welcome everyone to read our paper. And finally, this is pre-store. I hope you liked it. With this powerful technique, we proactively move data down in the memory hierarchy to avoid write amplification and to hide the cache coherence latency. We achieved up to 2.3 times performance improvement. Thank you, and I will be welcoming questions.